In this video, we continue with Unit 14, exploring what is the force exerted by a magnetic field, and we will do this by focusing on the first, on the one hand, on the force exerted on a moving charged particle, and then from there we will think of many moving particles making a current. So we will explore what the force on a straight segment of current carrying wire is. So the magnetic field is a vectorial quantity, as it was the electric field, and it's going to be responsible for the action at distance of the magnetic force. To denote it, we're going to use the letter B, and of course, as it's a vector, it will represent it as a vector. So the force exerted by this magnetic field on a moving charge is given by the following equation, where F is the force, Q is the charge of the particle, V is its velocity, and big B is the magnetic field. Okay, so this is the magnetic force exerted on a charged particle that moves at a speed V. Inside in a region where there's a magnetic field, and this is also known as Lorentz force. So if you remember, the force, the electric force, let's call it F sub E. The electric force on a charged particle was given by the product of the charge times the electric field. So there are certain similarities and certain differences between these two forces. So on the one hand, they are both proportional to the amount of charge. So the bigger the charge, the bigger the force. There is also another similarity that they're both proportional to the field. The bigger the field, the bigger the force. However, there's one big difference, and it's that the magnetic force needs the particle to be moving. Okay, so if the particle does not move, there is no magnetic force exerted on it. However, there could be, if there is an electric field, there will be an electric force exerted on the charge. There's also another important difference, and is this vectorial product. This is going to be different from the electric force, because in the electric force, the force is parallel to the electric field. The direction dependent on the charge. If it was positive, the force and the electric field had the same direction, and if it was negative, they were just had opposite directions. Okay, but here in the magnetic force, the force is going to be perpendicular to both the velocity of the charge and the magnetic field, because the force is proportional to the cross or vector product. So here you have it. The force has to be perpendicular to the magnetic field and also perpendicular to the velocity of the charge, which is quite different from the electric field and the electric force, and makes things just a little bit more complicated. So you need to remember now how to work with the cross or vector product. You have to go to your notes and try to remember. In many instances, we can use the right-hand rule. I don't know if you've worked with this, but there are at least two ways to introduce this rule. The first one I'm trying to show here with this slide is if you want to know what the cross product between vector V of the velocity and vector B of the magnetic field is, then you have to take your right hand and go from the first one, which is a V. You have to put your fingers pointing to the first one and move your hand towards the second vector that is inside this cross product. In this way, your thumb will give you the direction of the cross product of the first vector times the second one. This is a way of using the right hand rule for the cross product. Another one is with your fingers. So again, it's the right hand, and you have to get with your index finger, you have to point to the first vector, which in our case is v, the velocity. And then with your middle finger, you have to point towards the second vector, which in our case is b, the magnetic field. And in this way, your thumb will point to the cross product of both. Okay? There is here just something I want to point out, that the actual magnetic force is proportional to the charge. So if it's a negative charge, then the force is going to be the opposite to the cross product. Okay, so you first calculate the cross product of the velocity times the magnetic field, and then you multiply by the charge and take care of the sign of the charge. Because if it's positive, then the force is going to be parallel and in the same direction as the cross product of the velocity and the magnetic field. But if the charge is negative, the force is going to be towards the opposite direction. As it's the same as the case in the electric for the electric force. That the charge was you needed to know the sign of the charge. So again, this is I want you to try to remember how to do the cross or vectorial product. This is a way to do it when you have vectors. When v and b are perpendicular, it's easier to use. It's quite easy to use this rule. If they're not completely perpendicular, then they might be a bit more complicated. In the case they're not completely perpendicular, I suggest to first of all try to imagine what is the plane they both are in. So if you have two vectors which are not aligned, they both form a plane. Okay, so once you have this plane in your mind, you know that the cross product has to be perpendicular to this plane. Okay, because it has to be, the cross product is perpendicular to each of the two vectors entering this cross product. So once you have the plane, you just have to think of the direction perpendicular to the plane, and then to know if the cross product is going to one side of this direction or to the other, you need your right hand to apply the right hand rule. Another way is also using a mathematical approximation with the matrix and determinant. So you can go back to your notes of high school and take a look there. And also at the beginning of this general physics course, you had a reminder of how to calculate the vectorial product. If you find there is any problem, just write to me and I'll try to work them out with you. So this is a force on a moving charged particle, okay? Now we're going to think of many moving charged particles. We're going to think of an electric current. No, sorry, I was going too quick. So I had to discuss yet the unit of the magnetic field. So the unit we use is called Tesla, okay, in the international system. And if you get from Lorentz force, you can get what the relationship between these Tesla and other units are, because you can see that 1 Newton has to be equal to 1 Coulomb times the velocity, which is in meters divided by second, times Tesla. So if you get the coulombs and divided by the seconds, this is the ampere, which is the unit of the electrical current. So you get from here that 1 Tesla is equal to 1 Newton divided by ampere and meter. Okay, as it's also the magnetic field is a field, you can use field lines to try to represent it graphically. So these field lines look for a magnet. They look like this. So this gray area is the magnet, To the left you have the South Pole, to the right you have the North Pole. So the field lines of this magnet look like the lines that you are looking at here. And an interesting thing is that they come out from the North Pole and they enter the South Pole. And these, they have similarities and differences to the field lines of an electric field. So if you remember an electric field, the field lines began in the positive charges and they ended in the negative charges. This is not now the case because the field lines of the magnetic field do not begin nor end. They just they are loops. Okay, they completely closed loops. They just enter through the South Pole and exit through the North Pole. You can also trace them quite easily visually in reality by using iron fillings, as the iron fillings align along the field lines. There was just one thing I forgot to tell you about the units, that you can also use Gauss, which is another unit for the magnetic field, but it's not does not belong to the international system, because 1 Gauss is 10 to the minus 4 Tesla. And the use of Gauss is that normally the magnetic fields we experience here, the Earth's magnetic field is more of the order of Gausses than Tesla. Tesla is a big unit for the magnetic field. So now that we've seen what is the force acting on one charged electrical particle moving, we're going to look at what the force is on many particles that are on many charged particles that are moving. We're going to go now into a segment of current carrying wire. So you have to imagine, we have to go back to Unit 13, and you have to imagine that an electric current is really just a set of mobile charges moving through this wire. So in this figure, I try to present just a piece of straight segment. So this piece of straight segment has a length L here and has a cross-sectional area provided by A. Okay, so we have a current, an electric current flowing to the right. This is given by I. This is the electric current. So microscopically, what we have is small mobile charges that, if they are positive, if the mobile charges are positive, they would be moving to the right. We know that in wires, the mobile charges are really the electrons. So what we would have in an electric current that is going towards the right, we would have electrons moving to the left. However, it's just easier to think of positive charges moving, because you don't have to change signs. So we're going to think that we just have positive charges moving to the right. And if you remember our discussion of Unit 13, we said that in reality each particle is moving at a different speed, and they are accelerating and they are interacting and stopping when they interact with the ions of the net. But we can think of them as a whole of charges moving to the right at the same speed, which is an average speed, which is called the drift speed. Okay, and then I think I've introduced everything but the number density. Which we also worked in Unit 13. It's just the density, the amount of mobile charges that I have per volume, okay, per unit volume. So it's just a number per unit volume. So now we want to go from what is the force on one charge, that if you remember, the force on one charge is the charge, the value of the charge times its velocity times the magnetic field. So what we are thinking is that in this region we have a magnetic field, okay, pointing somewhat, and then for one of these charges, this one, okay, it's moving at the drift speed and has a charge Q, okay, so that would be the force on one of them. So if we have many, to know the total force on this segment of wire, we will just have to do to take the force on each of them okay, times the total number of charges that I have inside this segment, okay? How many charges do I have in that segment? Well, we know the number per volume, so we just need to multiply the number density, the number of mobile charges per unit volume, with the total volume. And the total volume here is just the area times the length. So the total force is going to be given by the force exerted on just one of these mobile charges times NaL, which is the number of charges we have inside that volume. Okay, so this you have a bit more clear here. This is where we went. And then you have to remember from Unit 13 that the electric current, the microscopic electric current was given, the electric current, the relationship with the macroscopic parameters I've been talking about here is given by the electric current is equal to the charge of each mobile charge times the number density times the area times the drift speed. So you can see that you have these here, okay? So we can relate this microscopic point of view to a macroscopic point of view, taking these as the intensity. However, there's a difference here that the intensity, if you remember, is a scalar and does not have really a direction. So we need still a direction to multiply with the magnetic field. So that's why the L is going to be transformed to an L, vectorial L. Okay. So from this equation here that is really dealing more with microscopic elements to this one here that is dealing with the macroscopic, with something we can measure. We can measure the electric current, we can measure the length of the wire, and we can measure the magnetic field. And the only thing is that now the direction of the current is given is provided in the vector L. So L is going to be a vector that has as a modulus just the length of the wire, and the direction is going to give you the direction of the current. Okay, so L would be a vector in this case that would point towards the right. Okay. So this is for a straight segment. What happens if you don't have a straight segment? What happens if you have an arbitrary shaped wire? If you have something like this, okay? If your wire is not straight, then what you can do is just evaluate what the force on each small piece is. So imagine this: we get a very small piece, so we can mark it with this little vector. So instead of being the big L, we're going to have a differential of L. Sorry, I was using capital L. So this is giving you the direction of the current at this point, and it would give you the direction of the current at this different point. So what we can do is calculate the force at each point, which would be provided by differential of F. Okay, so differential of F is going to be the force exerted on this little piece of wire, and it's going to be given by the whole current times the differential of length of this little piece of wire, and with the vectorial the cross product with the magnetic field. If you want to know the whole force acting on it, you just have to integrate the forces acting on each piece. Okay, there's I want to bring back the idea of the force exerted on just a single particle, which is this, to show you that there is a relationship. Okay, so here Q times v, the velocity, is in this other expression is I times ddl. Okay, so this measure of the charge and the speed and its direction for the Lorentz force for one charge is in, if you take a piece of wire, it's going to be, you are going to need, it has the same information as this that we call the current element. Okay, I want you to remember this because we will use it again in Unit 15. We will use the current element and we will pass from an expression that has something multiplying by Q times V to something that has the current element. Okay.